Today we're going to talk about volume again and also solids of revolution. So Cavallari's principle says that if you have two objects with cross sections that have equal area throughout the entire figure, that their volumes are going to be equal. So it seems obvious, but it's going to have some really nice implications as we try to prove the formula for the area of a ball. So let's look and see what the math language says so that we can interpret it correctly. If F and G are solids located between two parallel planes, pi and sigma, and if for every plane, gamma, parallel to and between pi and sigma, we have that the area of gamma intersected with F is equal to the area of gamma intersected with G, then their volumes are equal. So again, I'm looking between two parallel planes. I want to find that every plane that is in between the two and parallel to the two, if I look at the cross sections of the areas and the areas are equal for all of them, the volumes are equal. So now, thanks to Cavallari, we are able to derive the formula for the volume of a ball, as they call it in EMF. Everywhere else, you'll see it called the volume of a sphere. So this is actually pretty cool. And I have installed the model answer for exercise 58. So I want you to just work along with me. We're going to thoroughly define these two figures, and then we're going to see that as we take cross sections, that we're going to find some equivalencies between my cone and cylinder and the sphere. So we're going to let U be a length, let C be a right circular cone whose U radius and U height are both R. So I'm looking at this cone here. My radius is R and the height is also R. And that's for some positive real numbers. We're going to let the apex of C be A down here and let the center of its base be C. We're going to let H be a half ball with U radius R, so this half ball has that same radius here as my cylinder and cone do. And center of base B. Let S be a cylinder whose U height and U radius are both R. Let it be positioned in such a way that one of its bases is also the base of C, and C is a subset of S. Suppose that C and H are situated between two planes pi and sigma such that H's base is contained in pi and C's base is contained in sigma. So I have this plane here, sigma, plane here, pi. They are parallel to each other. The base of my cone is in sigma. The base of my half ball is in pi. And this cone is inside the cylinder with the same radius. Now we're going to let gamma be a plane that is both parallel to sigma and pi and situated between them. So you can see gamma is right here, and it's taking a cross section of my figure with the cone and cylinder, and also of my half ball. Now we're going to let x, that is a positive real number, be the perpendicular U distance between gamma and pi. So the distance between gamma and pi is x. We're going to let P be the point of intersection of my line AC and gamma. And we're going to let Q be the point where the line through B, perpendicular to gamma, intersects gamma. So I have my point P here that is x away from pi in my cone, center of the circle. And I have my point Q here that's x away from the center of my base. We're going to let R be a point of the intersection of gamma with the cone. So a point on the cone that intersects gamma, and we're going to let S be a point on the boundary of my half ball and gamma. Finally, we're going to let T be the point of intersection of sigma and AR. So A har is
is
here,
here,
T is over here, it's intersecting my plane sigma. Let's look more carefully at the solid that is the cylinder. So S is the cylinder. We're going to define N as the cylinder less the cone. So it's all this space outside of the cone. Now you can see that the boundary between the solid N and the cone is clearly a subset of the union of the boundaries. So we can use that property that says that I can add up the volumes of the pieces to get the whole. That's VO2. So the volume of S, which is the cylinder, is the sum of the volumes of N, the part outside the cone, and C. We can see that the line PR and CT are parallel. Therefore, when I look at the angle APR here and the angle ACT here, those are corresponding angles, so they're congruent to each other. And I can also see that PAR and CAT are equal as well, because PAR here and CAT are actually the same angle. So by angle-angle similarity, I have two similar triangles. Also, I can see that the side AP, the ordered pair, APPR, is proportional to ACCT. But AC is R, based on how we define that distance. And CT is also R here. That's the radius of that circular base. And we know that we've defined AP to be X. Well, if that's the case, then I know that PR is also X, because this is 1-to-1. I should have a 1-to-1 ratio here as well. So PR is equal to X. Therefore, gamma intersect N is the annulus whose area is pi r squared minus x squared. So really what we're looking at is this donut-shaped area. That's an annulus. So I have the outer circle and I have the inner circle. This distance here is x. That's my radius. From here to here is r. So if I find the difference between the areas, that's pi r squared minus pi x squared. That becomes pi times the quantity r squared minus x squared. Also, we can see that BQS over here is a right triangle with hypotenuse BS. And we know this hypotenuse is r because the radius of that half ball is r. And so we can use Pythagorean theorem. So x squared, that's this distance here, plus t squared is equal to r squared. If I solve for t squared, I find t squared is equal to r squared minus x squared. And therefore, the intersection of gamma with my half ball is a disk with square unit area pi t squared, or pi r squared minus x squared. Look how cool that is. These are the same. So the area of this half donut, or this donut shape here, is the same as this disk here. So those cross sections have the same area. So therefore, the two cross sections have the same area, just like what I said. Since this is true for every plane parallel to and between pi and sigma, we may conclude by Cavallari's principle that the volumes are equal. The volume of this outside my cone area is equal to my half ball area. So in view of this relationship between S, N, and C indicated above, it follows that the volume of N is equal to the volume of my cylinder minus the volume of my cone. The volume of my cylinder is pi r cubed. Remember, it's the area of the base times the height. The area of the base is pi r squared. The height in this case is r, so it's just pi r cubed, minus the volume of my cone. Well, the volume of my cone is 1/3 pi r squared. So that's 1/3 pi r squared times the height. Well, my height here is r. Simplifying, we obtain that the area outside this cone is 2/3 pi r cubed. So therefore, the cubic volume of the ball with u radius r is 2 times that, because this is a half ball. So 2 times that volume is 2 times pi 2 r cubed over 3, and that simplifies to pi 4 r cubed over 3, which happens to be the volume that we looked at earlier of a ball, 4/3 pi r cubed. Pretty cool. The next figure I'd like to discuss is called a frustum. A frustum is created by two planes that are parallel to each other, intersecting a solid figure, and then we take the space in between those two parallel planes to create what we call the frustum. This is a right conical frustum, and this is a pyramidal frustum. So let's define it more specifically. A frustum is a figure in space that is determined by a measurable figure S in space and two distinct planes, pi and sigma, that are parallel to each other, of which intersect S in at least one point. The frustum that they determine is the union pi intersect S and sigma intersect S, and the set of all points of S that are between pi and sigma. When S is a circular cone or a pyramid, the frustum is called a conical frustum or a pyramidal frustum, respectively. For each length u, the u height of the frustum is the perpendicular distance u between pi and sigma. The planar figures pi intersect S and sigma intersect S are called the bases of the frustum. So looking at this as a conical frustum, I have a circular base on the bottom, a circular base on top, and that's the part of the cone that intersected those parallel planes. The height of my frustum is the perpendicular distance here. This distance from this edge down to this bottom edge is called the slant height of the frustum. And I have the same kind of thing going on over here. I have a pyramid that was cut off. So I have a bottom base and a top base that are parallel and all those points in between. The volume of a conical frustum is given by this formula. So we're going to let u be a length, let r1, r2, and h be positive real numbers. Then the cubic unit volume of a conical frustum with base u radii r1 and r2 and u height h is 1/3 pi h times this quantity here, r1 squared plus r1 times r2 plus r2 squared. The next thing I'd like to talk about is a solid of revolution. To do this, you need to think about your figure. It's a two-dimensional figure, and then we rotate it around the line. So if you see that I have this rectangle here, and I rotate it with the one side of my rectangle attached to that line, what I produce is a cylinder. In this figure, I have a circle, and I rotate it around the line, and it produces this donut-shaped area here. And there's lots of two-dimensional surfaces you can rotate to create a three-dimensional solid. So we're going to let F be a measurable figure in a plane pi, and let L be a line in pi. Then the solid of revolution determined by F and L consists of all the points X, such that either X is an element of the line intersected with F, or X is a point of a circle that passes through a point F that is centered on a point of L and that lies in a plane that is perpendicular to L. The line L is said to be the solid's axis of revolution. Complicated words just for the idea that you're taking this two-dimensional area and you are rotating it around that line, and any point that that two-dimensional area touches as it rotates creates that solid. I'd like you to do exercise 60. Press pause on your video. When you're ready for the answer, press play again. Okay, here are the answers. So if we take and we rotate a right triangular region about a line containing one of the legs of the right angle, what we end up getting is a cone. So you can imagine that if I rotate this around, I'm going to end up with that cone figure, and it's going to be like that. For part B, if I take and I rotate a right triangular region about the line containing the hypotenuse, and you can picture that here, what I'm going to end up getting is the union of two cones. So the union of two right circular cones that share the same base. So this figure would rotate like that, and I'd end up with two cones that share the same base, letter D. For part C, if you rotate a half disc about a line containing its boundary diameter, here, what I end up with is a ball. It just rotates all around, and I create the full ball figure. If I rotate a half disc about the line, about its line of reflective symmetry, like I show here, what I end up getting is a half ball. For part E, and like what we saw on the previous page, if I rotate a rectangular region about a line containing one of its sides, what I end up with is a circular cylinder, letter A. For letter F, if you rotate a disc about a line in the plane of that disc that does not intersect the disc, what I end up with is what we call a torus. We saw that on the previous page. It's a donut shape. Letter G, rotate a trapezoidal region with exactly two right angles about the line containing the side that is shared by the two right angles. So you can picture that here, and what I end up with is a frustum. It's a conical frustum. And then finally, letter H, if I rotate a trapezoidal region with exactly two right angles about a line containing the longer of the two parallel sides, what I end up with is the union of a cylinder and a cone. So if you can picture this rotating, this part that would make up just that rectangular part would be the cylinder, and then the part that is the triangle would represent the cone. Here's another definition: a cross-section of a solid of revolution. We're going to let R be a solid of revolution whose axis of revolution is the line L. Then a figure F is a cross-section of R if and only if F is not the empty set, and for some plane pi such that L perpendicular to pi, F equals R intersect pi. So let's draw a picture of what this is. So if you imagine that you have a rectangular area, like what we showed on the previous section, rotated around this line, what's created is a cylinder. And when we talk about a cross-section, in order to be considered a cross-section, I have to have a plane that's perpendicular to this line. And what ends up happening is that cross-section is the two-dimensional shape that's formed by the intersection of my plane with my solid. So in this case, this particular cross-section would be a circle. So again, according to our definition, that plane that's intersecting my solid must be perpendicular to the line that is defining our revolution. So again, the intersection of the plane with that solid figure is considered a cross-section. I'd like you to try exercise 61. Press pause on your video. When you're ready for the answer, press play again. So if I have a triangle, right triangle, with my right angle at C, and it's rotated around this line AC, what I create is a right circular cone. One cross-section of R consists of a single point. Which point is that? Well, it must be A, because that's the only place where I could draw a plane perpendicular to this line of revolution that would intersect at only one spot. So it's point A. Part C says, apart from the single point cross-section, every other cross-section of R is what kind of figure? Well, every other cross-section is a disk of varying radii. And then part D says, one cross-section of R has a square centimeter area of 9 pi. Let the point where this cross-section meets AC be X. So I drew that over here. That's X. And they ask, what's the centimeter length of CX from here to here? Well, if my area is 9 pi, that means my radius has to be 3. So what I'd like to know is how far this point X is up on my segment AC. Well, looking at this, I have created two similar triangles, so I can set up a proportion. So I called the distance between C and X lowercase x. I don't really like how I wrote that. Let's try that again. Lowercase x. So that, again, is this distance between A and X. And I set up a proportion that says 10 is to 4 as X is to 3. And then I cross-multiplied and I solved for X. I found that was 7.5. Well, this is not the distance I'm looking for, although now I know it's 7.5. The distance from C to X is 10 minus 7.5, so that becomes 2.5. Now I'd like you to work on exercise 62 and the volume practice worksheet that I've posted online. Have a great day.